Welcome everyone again to another seminar of the another session of the data learning seminars. Today we have Professor Stephen Brunton from the University of Washington. A bit of a bio: he did his bachelor's in Caltech and his PhD in Princeton. And yeah, to everyone, I really enjoy your YouTube videos. I have to say that. And yeah, that's the main reason why I wanted to invite you to, so everyone can learn about your work. So I'll leave the audience with you.
Wonderful. Thank you all very much for the invitation and for the introduction. So it's really a pleasure to be here virtually. Hopefully next time I'll see you all in person. London's one of my favorite cities in the world. So I'm excited today to tell you about some of the work that's happening in my group and in my larger collaborative network on using machine learning for scientific discovery. Before I jump in, I want to acknowledge many excellent co-authors, colleagues, and collaborators on these various projects. And especially in the middle row, I want to acknowledge my excellent postdocs and graduate students who have done the majority of the work I'm going to tell you about. And actually, if you're interested in some of the fluids work, you should talk to George Regas, who is a faculty at ICL. And so you can chat with him about things like that. So I want to start. This talk is going to be about the intersection of machine learning and dynamical systems. How do we use modern tools in kind of data-driven optimization and machine learning for better modeling and control of complex systems? And so I want to kind of demystify what I'm talking about. So I think with this group, you have a really good handle on what machine learning is, what optimization is. But often I give this talk to, business leaders at Boeing or Airbus or Lockheed, where they know that machine learning exists and that it's important, but they might not know exactly what it is. So my working definition is that machine learning is kind of a superset or an umbrella that encompasses building models from data using either optimization or regression. And when we think about it this way, it becomes clear that we have been doing things that are in the framework of machine learning for decades, if not centuries. So if you think about the Kalman filter from the 1950s and 60s, that's absolutely in that umbrella of machine learning. We're building models from data using regression and optimization. But our tools are much, much better now. We have faster computers, more data, better applied mathematics tools, and optimization algorithms. And so it really has been elevated tremendously even in the last 10 years. And so in blue, you see the tasks that I think about on a daily basis. And I'm going to give a lot of examples from fluid mechanics because that's my core physical domain of interest, is in unsteady fluid flows like the atmosphere or like when you stir cream into your coffee. But what I'm going to say really applies to any complex dynamical system. So I'm going to work on fluid flows, but if you're interested in epidemiology, how a disease spreads across a continent, or neuroscience, how the network of neurons in your brain combines to form consciousness and make decisions, those are also dynamical systems that are high-dimensional, nonlinear, and multi-scale. And so some of the tasks that we care about in blue, we try to reduce the dimensionality of those problems. So all of those examples I gave you, neuroscience, disease modeling, and fluid flows, typically involve millions or billions of degrees of freedom to model these in a computer. And we want to reduce that dimension to find the core essential latent variables, or the manifold where the data lives. We also want to build models in those reduced coordinates and also learn how to sense sparsely. So sparse sensing is really important in engineering applications. How would you place, if you had 5 sensors, where would you place those 5 sensors to listen to that very, very high dimensional system and gain as much information as possible? And finally, some of the other goals are focused on control and estimation. You actually might want to manipulate the behavior of the system in neuroscience to suppress seizures, perhaps, or Parkinson's disease. Maybe in epidemiology, you'd want to suppress an epidemic that's spreading across a continent. And so every single one of those tasks in blue you can think of as an optimization problem. These optimization problems are nonlinear because the equations of motion are nonlinear. They're multi-scale in space and time because the physics of the situation are multi-scale. And that leads to very high dimensional non-convex optimization problems. And so that's what I really want to start this talk with, is that all of the problems I care about in blue can be phrased as challenging optimization problems in pink. And those optimization problems are exactly what machine learning is getting very good at handling. So if you think about training a neural network, that is a high dimensional non-convex optimization problem that we've gotten very, very, very good at solving. And so we have some hope of applying these new techniques to these classically challenging dynamical systems tasks. Now, why do we believe that we can do these tasks? Why do we believe that we can model and control fluids or understand a network of neurons or a disease system? And I would say that the fundamental reason why we believe that we can approach these physical problems with machine learning is the same reason that we believe we can do machine learning at all. It's because there are patterns that exist in your data. So even very high dimensional data like this video of cloud formation over Guadalupe Island, again, this would require millions, if not billions of degrees of freedom to simulate in a computer. And the movie has, 1 million pixels. But you can see with your eye that there are low dimensional patterns that are emerging in this system. And those dominant patterns are what facilitate the machine learning process. It's what facilitates dimensionality reduction, reduced order modeling, and optimal sensing, estimation, and control. And if you're interested in this, we actually wrote a review paper recently. This is with Sam Tyra from UCLA, where we investigate kind of how to extract these patterns for complex high dimensional systems like fluid flows. Okay, so that's the starting point. We believe that there are patterns that exist, and those patterns facilitate all of the learning tasks, the downstream learning tasks that we're going to achieve. So this is how I organize the work in my lab, and kind of my thoughts this is a classic control diagram for any of you who have done kind of control optimization. The blue box contains all of the systems we're analyzing. All of the systems I care about are fundamentally dynamic in nature. They change in time. The brain, a fluid flow, the climate, these are all dynamic systems in that blue box. And I want to model those systems, but I don't just want to model them. I also want to control them. I want to manipulate their behavior for some kind of an engineering nominal objective. For example, if I can control a fluid flow better, maybe I can increase the lift and decrease the drag on my aircraft or on my transportation boat or truck or train. And even a small amount of improvement in our ability to model and control turbulence could have hundreds of billions of dollars of economic impact and greenhouse gas reductions and things like that. So a lot of what we do is apply machine learning to model these complex systems. So a lot of the systems I care about, there are not first principles equations of motions. There's no textbook equations for your brain. And so we have to learn them from data. And so a lot of what I'm going to talk about, this is about 50% of what my lab works on, is how do we learn physical models from data? How do we learn equations, differential equations of motion that are interpretable to humans and that generalize better, for example, than neural network architectures? Another big aspect of what we do is to directly apply learning to build effective controllers. So for example, in this cross-flow turbine example, we put these turbines in large rivers, for example, in Alaska, where it's difficult to run power lines. And we can use genetic algorithms or other kinds of machine learning optimizations to learn through trial and error effective control strategies to harness that fluid flow to generate as much power as possible. I believe in this case, we extracted about 60% more power than the industry best algorithm just by applying simple machine learning optimizations. And reinforcement learning would also fit in this box of learning controllers by trial and error. And then the third big thing my lab works on is using optimization, kind of data-driven optimization, to learn effective sensor and actuator locations. So again, in these high-dimensional systems like a brain, where would you put sensors and actuators to best inform a model or a controller? And I'm going to go on a little tangent here. For most of what I'm going to talk about today, I'm actually going to talk about this block of learning dynamical systems from data. This is kind of how digital twins fit in. So we're going to learn models of components of systems that can fit together. So kind of, some digital representation of your system. But I'm going to take a little aside to tell you about the sensors because it's so interesting. So again, the reason we think we can measure a really complex system like an unsteady turbulent fluid flow with 5 or 10 or 50 sensors is again because patterns exist in the data. And we've learned a lot from biology. So I actually started working on this problem with my wife, Bing Brunton, who's also a professor. She's a professor of neuroscience at the University of Washington. And we started looking at this problem of insect flight. So when insects fly, they flap their wings and they interact with extremely complex, unsteady flow environments. Again, beyond our ability to simulate some of these turbulent flows that they interact with. And it turns out that all flying insects have about 50 to 100 strain-sensitive neurons on their wings. These are neurons that fire depending on how the wing bends. And these insects can detect subtle flow patterns on their wings with these strain-sensitive neurons and use those to inform their flight control decisions. And it turns out that they actually can make decisions faster than that information goes to their brain and back to their muscles, which is strong evidence that they're doing local computations in their shoulder muscles. And so this is the kind of thing we would want to do as engineers. We would want to sense these very, very high dimensional complex systems with a few sensors. And we'd like to make fast local control decisions that, for how to interact with these environments. And again, that all relies on the fact that patterns exist. Out of all of the possible configurations the fluid flow that it's interacting with can take, there are a few dominant flow patterns that affect the moth's daily life, like leading edge vortex and things like that. And so we actually use this technology. We developed a mathematical framework for where to place sensors. If there are patterns that we have learned, where would you place sensors to maximally estimate what those patterns are? And it turns out that same mathematical architecture applies to a huge diversity of other problems in engineering. So this is a really interesting problem. We worked with Boeing about 5-6 years ago. Every single aircraft that's built today, every commercial aircraft built by Boeing or Airbus is held together with about 1,000 to 10,000 custom-made shims. This is a crazy fact. I didn't know this until I started working with Boeing. Shims, just like when you have your table and it wobbles, you put a shim under the feet. That's what the kind of shim I'm talking about. So even though these aircraft are built to very exacting tolerances, when you assemble these huge structures, large gaps start to form. They can be even up to 1 centimeter gaps between where the pieces should be and where they are. And so you have to measure every piece with a laser scanner, calculate what all of those gaps are, manufacture a bunch of custom shims, and then build the aircraft. And it's a huge extra cost for this measurement and shimming. And so it turns out that Krithika Manohar, pictured below, leveraged this sparse sensor algorithm that we learned from the moth and developed an analog for Boeing where they can measure very, very few points on their wing and figure out what those shim distributions are going to be. So this technology, it turns out, has already saved Boeing hundreds of millions of dollars on multiple aircraft. So this is in production today on the 777X, the 787, and the 737. So that's kind of a cool story of how basic research on trying to understand how biology does something can actually have huge impacts in engineering if you find the right kind of mathematical formalism. And again, this is just optimization, sparse optimization with data. Okay, good. That was a little aside. So now for the rest of the talk, what I'm going to do is I'm going to talk about how we build dynamical systems models from data that are as physical as possible. They give us physical insight that allow us to control the systems, understand the systems purely from data. And so to start, I'm going to give you a little kind of a warm-up story. This is with Jared Callahan and my other colleagues, where essentially what we're trying to do is learn dominant balance physics relationships from data for complex systems like turbulence. And I'm going to define what I mean here. So you don't have to know anything about physics or dominant balance or fluids. This video here is a turbulent boundary layer. This is an open source data set from Johns Hopkins University. And this turbulent boundary layer is analogous to the flow you would see over a wing of an aircraft. Dominant balance refers to this observation. So before we did computational science, back in the 1940s and 50s and 60s, when computers were relatively new, to study complex systems like this turbulent boundary layer, you would take the governing equations, the Navier-Stokes equations, which have a lot of terms, maybe 64 terms in this partial differential equation. And what you would do is you would make physical arguments that in certain regions of space and time, some of those terms are nearly zero, while a subset of the terms are kind of dominant and kind of balancing each other out, equal and opposite. They're balancing the equation with a few subterms of the equation. And that would allow you to simplify the equations enough that you could work out solutions by pencil and paper by hand. And in fact, in the United States, this is where most of our applied mathematics departments were born, is to do dominant balance asymptotics on these kinds of fluid flows before computers. So in the US, this is where applied math departments came from, is this dominant balance analysis. And we still do it today. It's just much less common because we have powerful computers that can solve all of the terms of the equation. And so what we're going to do here is see if we can build an automated, a data-driven kind of machine learning way of finding these dominant balance relationships purely from the data. Okay, so we're going to take this Johns Hopkins data set, and the first thing that you would generally do for a fluid flow is you would take a two-dimensional slice in the middle and you would average in time to get these Reynolds average Navier-Stokes equations. So this is an equation with 6 terms you can see here. And we want to find, are there regions of space where different subterms are equal and opposite while the other ones are 0? And so you can plot, you can actually calculate each term. This term here, you can compute this term at every point in space and plot it. This is what the u bar x term looks like in space. And you can plot all of the terms. All 6 terms you can compute and plot in space. And you'll see just by eye already, there are clearly regions of space where the terms, where a subset of the terms are large and equal and opposite, and other terms are nearly 0. So the dark regions are nearly 0. I think blue is positive and orange is negative. And so Jared Callahan had the really interesting observation that every single point in space here, for every pixel in these two-dimensional images, there are 6 numbers that you can compute, these 6 terms in the equation. And so you can plot every point in space in this 6-dimensional equation space. You can do a scatter plot in 6-dimensional equation space where each axis is 1 term in this equation. And when you do that, these are two-dimensional slices of the data in equation space. You can see immediately that the data is living on these subspaces where certain terms are approximately 0 while other terms are in a balance with each other. So we're going to automatically extract these balance relationships by first applying a rudimentary clustering algorithm. This is just a Gaussian mixture models to find these different clusters. And then trying to find a sparse subspace identification for each cluster. So for example, for the red cluster of points, I want to find a subspace with as many 0 components as possible. That's what I mean by a sparse subspace identification. And we do that for the red cluster, the blue cluster, purple, orange, green, and so on. And when you do that, you find that each of these clusters of data are really well described by a subset of the terms of the physics. So the red cluster only has 2 terms, the blue cluster has a different 2 terms, and so on. And for each of those red points and purple points and orange points, those corresponded to somewhere, a location in space. And so we can replot them back in space. And essentially what we do is relearn that there are these important physical layers of the boundary layer. This is, again, flow going from left to right over a wing. And we learn that there is a viscous sublayer, an inertial sublayer, a transitional region, these different regions that have different pieces of physics that are dominant and balancing each other out. So there's a lot you can do with this. You can build faster simulators. You can do matched asymptotics at the boundaries. And these are models that are interpretable to humans. I can show this to a fluid dynamicist and point to this red region and say, look, I see this region here that has these terms in the physics. Does this mean something to you? Now, we've known the boundary layer physics for the last, almost 100 years. This is one of the most well-studied problems in fluids because it's how we build aircraft. But we decided to apply this to a lot of systems where we don't know the answer. So we've applied this to supercontinuum optics. This is basically really high energy lasers. We've applied this to geophysical flows, like trying to understand climate balances in the Gulf of Mexico. We've discovered some interesting kind of different local balance regions where different weather would occur. And we've also applied this to neuroscience problems where we try to essentially cluster or segment different regions of either a neuron or a brain based on the local physics that's active. So I'm really, really excited about this. This is pretty new work. And I think that this is a really great entry point to applying machine learning to physical systems, because this gives you very interpretable models and pictures and a lot of information that domain scientists will find useful. And the other nice thing is, if you have data and you can compute derivatives, you can make these equation space plots. You can make these plots, you can cluster the data, and you can start to segment your data based on what is physically active, what terms in the equation are physically kind of large and in balance. So very, very exciting, exciting work. Now, that was kind of a warm-up for the next big piece of this talk, which is how do we actually build dynamical systems models for these complex systems? So that was one piece. Now what we're going to talk about is, if I have some complex system like a brain and I've got measurements in time, or a disease spreading across a continent, or this fluid flow past a truck driving down the highway, how would I build a reduced order model, some differential equation x dot equals f of x, that gives me as much information about this complex system with as few degrees of freedom, as little effort as possible. Okay, so that's going to be kind of the second half of this talk. And at this point, I want to kind of take a step back and talk a little bit about the philosophy of what kinds of models do we want? Because if I have data like this, I can always train a neural network to, based on this data. And if I have enough data, I can get pretty good predictions. I can get models that will generate a movie that looks a lot like this, but I won't always get a differential equation x dot equals f of x that I can use for control, that I can explain to a human. And I think this is really important to have these kinds of models. So I want to emphasize that there is a critical need for machine learning models that are both interpretable and generalizable, especially when we use these systems for safety critical engineering tasks like designing aircraft or autopilots for autonomous cars, robots that work in factories next to people. We need our machine learning solutions to be interpretable and generalizable. We can't just have opaque neural network solutions for everything. Instead of defining what I mean by interpretable and generalizable, I want to give an example. So my favorite example is Newton's second law, F equals ma. So this is clearly interpretable because it's very simple. There are three terms in the equation, F, M, and A. They have units. You can write down this differential equation for a particular physical problem of interest, like a pendulum or an automobile, and you can go to the coffee shop with your friend and analyze the terms. They have units, okay? And it's generalizable in the sense that you can learn F equals ma from an apple falling on Earth. At least that's how the story goes. And this law is still true when we land humans on the moon. That's incredible. That's a really incredible power of generalization, that this model can be learned from an apple falling on Earth. It's still true when we leave our planet. And you could build a neural network based on data from apples falling. You could take videos of apples falling And you might need 5,000 of these videos, but if you had enough data, you could train a neural network to generate new videos of new apples falling that no human has ever seen, that would probably fool all of us. But that model will not be useful when we decide to land humans on Mars. Okay, that will not generalize. And so I want this kind of equation here, F equals MA, more than I want a neural network that just reproduces the training data. Good. And this has been a principle in physics since basically the beginning of physics, since ancient times. We had this principle of parsimony, that kind of the bit of a system that generalizes is what we call physics. Physics is the part of a model that generalizes to new scenarios. And typically from Aristotle to Einstein, we have defined what is physical by the model that is as simple as possible, but no simpler. This is Occam's razor, this is Pareto's 80-20, this is the principle of parsimony. And again, this has been how we have defined what is physical from Aristotle through Einstein. And today in the mathematical era, we have some tools to promote these kinds of models in our machine learning models. And the two biggest tools I think of that I use on a daily basis for this are trying to build models that are low dimensional, that have as few variables as possible, but no fewer, and sparsity, building models that have as few mechanisms, as few terms in the differential equation as are needed to describe the evolution, the interactions, but no fewer and no more. And so low dimensionality and sparsity is how my group develops machine learning models that are interpretable and generalizable. And I'll point out that we actually use this architecture quite a bit, this kind of deep autoencoder neural network for dynamical systems, where our original variables X might be, measurements of a brain, and those might not be the right measurement coordinates. So we have to learn a coordinate transformation into some new system Z, where we can learn the dynamics, Z dot equals F of Z. So there's this kind of joint problem of learning a good low dimensional coordinate system Z, and then learning a sparse differential equation F in that coordinate system. And if you can learn a model like this from your data X, oftentimes this model will generalize better and be more interpretable than if you just trained an end-to-end neural network. Okay, so if we fast forward to the computational era, we want models that look a lot like this Lorentz 1963 model. So for example, if I have data from a complex system like this chaotic thermal convection, this is like weather in the atmosphere. That's what Lorentz is modeling, is kind of boundary layer weather in the atmosphere. Even though the physics is very complicated and high dimensional, Lorentz was able to write down a very simple model. It's low dimensional because it's only written in terms of X, Y, and Z, which are the amplitudes of 3 spatial modes that are used to describe this complex chaotic system. So it's low dimensional, and it's sparse in the sense that on the right-hand side, out of all of the possible terms that could describe the differential equation, this is very simple. There's only 7 terms, 5 of them are linear. It's about as simple, as sparse as you could get away with to represent this chaotic dynamical system. And so these are the kinds of models that we want. Essentially, what we want to do is build an automated Lorentz type model. And so that's what I'm going to tell you about now, is how we have essentially used sparse optimization, really simple machine learning tools, to build these types of Lorentz models purely from data. And I'm actually going to warm up on this Lorentz problem. So we're going to pretend as a warm-up, this is the sparse identification of nonlinear dynamics, or SIND algorithm. We're going to pretend that we have data from this complex system, but we don't know what the equations are. So we just measure X, Y, and Z. We think there are equations, but we don't know what they are. Now, by far the simplest thing, if you measured X, Y, and Z, and let's say you can compute the derivatives X dot, Y dot, Z dot, the simplest model you could build would be a linear model, like the dynamic mode decomposition, a little 3x3 linear model that best fits X, Y, and Z dot to X, Y, and Z. But we know that that model is going to be a poor description of this rich chaotic system. That little A matrix, that linear model, that linear regression model, has a single fixed point at the origin. It does not have it can't describe the complexity of this chaotic system with multiple fixed points, multiple unstable periodic orbits, and chaos. And so instead, what we do is we augment the right-hand side with more terms that could possibly describe these nonlinear dynamics. So instead of just x, y, and z, we add terms like x squared, xy, y squared. In this case, polynomials up to 5th order. Very important. We're not limited to polynomials. We can include anything we like in this library. I'm just using polynomials for illustration because it's simple. And so now what we're trying to do is find the fewest terms in this library, the fewest terms on the right-hand side that add up to equal x dot, that add up to equal y dot, and that add up to equal z dot. Now, 20 years ago, this would have been a combinatorial brute force search. You'd have to check every single combination of a few columns of theta to see if it worked, to see if it equaled x dot, y dot, and z dot. Now there are convex relaxations, convex optimization algorithms that are with high probability going to solve this problem, the sparse regression problem. And we leverage those for this. And when you find the fewest terms that add up to x dot, y dot, and z dot, you find that you actually can write down this differential equation, x dot equals sigma y minus sigma x, and so on and so forth. And the structure of the equation we learn is identical to the dynamics that generated the data. Again, we only started with data. We didn't know the equations, and we're learning them purely from the data. So this is a nonlinear system identification task. And this is one of the, at least when I was a graduate student, this is one of the big open problems in the field, is how can you learn nonlinear differential equations purely from data? It turns out sparse optimization is really key to doing this. So if you're interested in trying this, we have open source code, PyCindy. It's really well developed and well maintained. And you can basically apply this to any time series data that you have to try to learn these nonlinear dynamical systems models. I'll also point out that you can apply this to partial differential equations. So what I showed you before was learning ordinary differential equations with just a time derivative, like the Lorentz systems. But you can also use this for learning partial differential equations. This is work by Sam Rudy when he was a PhD student with Nathan and me. So if we have spatial temporal data, data that varies in space and time, like climate data, weather data, this fluid flow data, you can build a similar library regression procedure where now the right-hand side does not just include nonlinear terms, but it also includes partial derivatives. Subscript here means partial derivative, like omega x is partial omega partial x. And so you can set up a similar sparse regression problem to find the fewest terms of this library that equals partial omega partial t. And when you run that sparse optimization, you actually learn a partial differential equation. And it turns out that our identified dynamics are identical to the Navier-Stokes equations. And in fact, we learn the term that is 1 over the Reynolds number to within about 1%. This is amazing. If I just had data from a fluid flow, I could learn that the Navier-Stokes equations are the most consistent model that describes that data. Now, there's also, because there's so much spatial temporal data, you can get away with massively subsampling and still find these models. Now, I should point out, if all that we did was relearn the Navier-Stokes equations, that wouldn't be that interesting. We already knew them, right, for the last 150 years. This is a proof of concept that from data, you can learn complex physics. And since writing this paper, our group and our colleagues across the world have been using these to discover entirely new physics that's never been written down before. So for example, if you apply these to plasma physics, magnetohydrodynamic systems that are more complicated than the Navier-Stokes equations, you can learn partial differential equations with new terms that have never been written down before that describe these complex plasma interactions. You can apply these to climate systems, to ecological systems, to brain systems, to learn differential equations that have not been written down before. Good. And so just kind of a high-level summary, what the Cindy procedure does is it takes data and generates dynamical systems that are interpretable and that generalize, that apply to other scenarios. Think about the fluid flow example I just showed you. I could take one fluid flow, I could learn the Navier-Stokes equations. That equation applies to all fluid flows. That's a huge generalization capability. So the types of dynamics we might want are ordinary differential equations or partial differential equations. And we've shown that we can go from something like Lorentz to the Lorentz equations, or something like a fluid flow to the fluid flow equations. We can also get reduced order models. So if I don't want a partial differential equations, I can approximate this fluid flow in a low dimensional subspace, X, Y, and Z, the amplitudes of these modes, and similarly generate ordinary differential equations in that subspace. Okay, good. So that's actually what I'm going to show you next is that last row. And I should point out, if anyone has questions, please feel free to interrupt. I think this is actually a pretty good place if anyone has questions, because I am about to go even deeper down the rabbit hole. Anybody? I'll just wait for 15 seconds.
Yeah, so sorry, if you have any questions, just like raise your hand. Marta?
Hi. Hi. Thanks very much for the talk so far. It's been really, really interesting. I was wondering, the Lorentz system has chaotic solutions like the one you're showing us now. So Cindy is able to find the coefficients as well as the form of the system of ODEs in this case. But will that mean that because of the errors in the approximations of the parameters that the system will diverge quite quickly from approximations? How do you, from the data, if you let it run in time, and how would you cope with that?
Yeah, that's a really good question. So this system, yes, it is fundamentally chaotic. And that does pose some challenges, but it also gives us some opportunities. So the challenge, as you mentioned, is that even if we have a very good model, the model and the truth will diverge kind of exponentially quickly from each other. But if you have a correct model, it will stay closer to the true solution for longer than a bad model. I think that's an important point, is that if we had the wrong model, it would diverge even faster. And if we had the correct model, what you can do is something like you could Kalman filter. So if you have occasional measurements, you could assimilate those measurements into this model and essentially repin the model to the true trajectory. This is what climate scientists do. So these models are still useful. Even if I had the exact Lorentz model and I changed sigma by 10 to the minus 15, eventually that will diverge, but it's still useful to have the form of the model. You can get good statistics of statistics on the attractor, things like that. And then I'll also point out, for learning the dynamics, having a chaotic system is actually really helpful, because the longer I collect data, the more data I collect, it never goes back to the same place exactly. So I always get more information. The longer my trajectory, I always get more information from a chaotic system. Great question. Thank you. Other questions?
I don't see any more raised hands.
Okay, good. So we talked about the first row and the second row. Now I'm going to talk about how to build these reduced order models. And this is a huge field in fluid mechanics. So reduced order modeling is about 50 years old. Actually, it goes back to Lorentz, right? Lorentz was doing reduced order models of fluid flows, but it really came into its own in the 1970s and 80s. And it is a really important tool for designing aircraft and aerospace structures, engines, and also for controlling them. So we're going to look at how to build reduced order models of systems like this flow. And we've known for a while, Bernd Nowak told us that there is this great coordinate system given by those modes on the left. So if I take this fluid flow and I break it into those three modes, I can essentially build a differential equation in terms of the amplitudes of those modes, X, Y, and Z. So X and Y are POD 1 and 2, and Z is the shift mode. And if I took the actual partial differential equations and I projected it onto this subspace, this is the differential equation I would get. Now that's very, very laborious. This is what's called an intrusive computational model, where you actually have to have a working numerical code. You have to be able to get into the guts of the code and decompose all of the pieces, all of the terms of the equation to build this model in Blue. It's very, very time consuming. It takes at least one PhD year typically to build these models. But if we just measured the system and project and measured the system amplitudes X, Y, and Z from data, it turns out you can learn these models with Cindy without doing that intrusive, one PhD year worth of work. You just build the library, do the regression, and you learn that blue model without ever having a working code, a working numerical simulation of the fluid flow. And our identified system has the same basic structure and dynamics observed in the high dimensional system. So this is pretty cool. We showed this in our first paper on Cindy, but then very quickly after, Jean-Christophe Loiseau from Paris Tech we started working together, and he had two really key innovations that massively improved our ability to handle these systems. So the first innovation I think is really important because this bears on physics-informed machine learning. He pointed out that we actually know a lot of partial physics of the system, of these incompressible flows. We might not know what exactly the model is, but we know that all of these systems conserve energy. And we know that they conserve energy through a skew symmetry of the quadratic terms. The quadratic terms have a skew symmetry that is how we enforce energy conservation. And so he essentially added one line of code to our optimization that allows us to enforce these symmetries by construction, so all of our models conserve energy. That's a huge innovation. With just one line of code and a simple partial knowledge of the physics, when we bake that into our models, we immediately get more stable models and models that are better conserving energy. The second innovation was, instead of just having quadratic terms, so the Navier-Stokes fluid flow equations only have quadratic terms, so we tried building libraries with quadratic terms. But if you allow yourself to have third and fifth and seventh and ninth order terms, higher order terms, you can account for truncated energy. You can essentially build closure models for low energy structures that you're neglecting. So I want to show you how this works on the cavity flow and the cylinder flow. So what you see in the right column here, in white, this A delta is essentially the drag coefficient. It's a quantity we care about as engineers that we want to model. It's the drag evolving in time. And the yellow and blue are the industry standard best POD Galerkin models, the best classical models. You'll see that they qualitatively are okay, but quantitatively are pretty inaccurate. They have overshoot, they have the wrong rise time, and they have steady state error. But when we apply Cindy to model the system using either the constraints or the cubic nonlinearities that JC developed, we can quantitatively almost perfectly capture this drag coefficient. So we have better, less overshoot, no steady state error, and very, very close rise time. So these are extremely accurate models, more accurate than the previous models and simpler because we're just using regression. And I think the point that I want to make, the most important point here, is that because these models are sparse by construction, they're simple by construction, you can write them down on a napkin and take them to a cafe in Paris and analyze them. This is what JC did. And he came up with this equation for the cylinder flow. This is literally the differential equation that gives that nearly perfect model agreement in the lower right panel. This is, to date, the simplest and the most accurate model for this complex fluid flow that's been written down. And so I think that's kind of the power that you can get out of sparse modeling, is that it's not just accurate, but it's also very, very interpretable. One last thing I'll point out about this is that you can also get away with, if you don't have full flow field measurements, if you only measure the lift and drag on the surfaces, this is much more like what Boeing or Airbus would have, is just lift and drag measurements. You can build these sparse nonlinear models directly in those lift and drag coordinates, which is pretty cool. So the bottom panels show that our true simulation in yellow is almost perfectly captured by our low order Cindy model in blue. And all we're measuring is lift and drag coefficients. Okay, so in everything I've shown you so far, we knew the right coordinates to measure the system. In the Lorentz example, we measured X, Y, and Z because that's what Lorentz did. In the fluid flow example, we measured those three modes that we knew from classical models. Here we measured lift and drag. What if we don't know the right coordinates? What if I have a video of a system, or I have just a patch of recordings in a brain, and I don't know what the right coordinate system is? So that's where the deep autoencoder networks come in. And this is, I think, a really nice way of using neural networks for their full power without kind of losing insight or generalizability or interpretability. So the goal is, if I have very high dimensional data X, I can build an autoencoder down to a latent space Z so that I can reconstruct as much information about X as possible. This is a really good way of getting a manifold or a low dimensional representation in Z for the high dimensional data in X. And so a lot of what we do is try to learn these autoencoders so that we can get dynamical systems in that latent space, Z dot equals F of Z. So we build an autoencoder so that we can get SIMD models in the latent space. And I'll point out that in lots of cases, you can't get a good sparse model F until you find the right coordinate system. So if you go back to classical planetary motion, celestial mechanics, like this is the origins of much of our understanding of the universe and of science and mathematics, is looking up at the night sky. So if we look up at the night sky, this is what we see. We're the blue dot in the middle, and we see all of the planets moving around us in very kind of erratic patterns. Sometimes Mars turns around and goes retrograde. There's weird patterns that are hard to explain. And until we put the sun at the center of the solar system, until we apply a coordinate transformation into a new coordinate system, the heliocentric coordinate system, it's very hard to learn F equals ma on the right. It's easy to learn F equals ma on the left. So this is really important. To get those parsimonious interpretable models, we often need a good coordinate system first. And so that's what Kathleen Champion did when she was a PhD student working with Nathan and me, was essentially to combine autoencoders for good coordinate systems and SIMD for parsimonious modeling. And what she showed was essentially that for very high dimensional data, like you would get from a video stream, from a GoPro camera, you can learn good coordinate systems and sparse models if you design the right loss function, the right cost function to optimize over. Turns out this is a pretty stiff optimization problem, and it's a pretty complicated loss function, but it is possible to learn simultaneously good coordinates and sparse models. Okay, good. So that's kind of what we've done here, is learn these dynamical systems models and the coordinates directly. And what I'll point out is that you can add even more stringent constraints on F. Instead of saying F has to be sparse, you could say that F has to be linear. Now that's a lot of constraint. That's very hard to find a coordinate system where your system becomes linear, but they do exist. This is related to Koopman operator theory. And so Bethany Lush, when she was a postdoc with us, actually developed this Koopman autoencoder network that would essentially find a coordinate transformation of a very nonlinear system into a new coordinate system where it looks linear, where it's defined by just a linear operator K. And this is nice because even though finding that coordinate system is very expensive, very challenging, once you find that coordinate system where the system is linear, all of your tasks afterwards are much simpler. This is essentially one line of Python or MATLAB code for optimal linear control, optimal linear estimation, optimal linear sensor placement. And so this offline task of finding this coordinate transformation enables really, really easy online sensing, estimation, and control. So if you're interested in this linearization of nonlinear systems, it's related to Koopman operator theory. We just wrote kind of a monster review paper. This is like 110 pages of Koopman theory, everything you'd ever want to know about these coordinate transformations and how to use them. But the kind of moral of the story is that you often can learn coordinate systems so that your dynamics are either sparse or in some cases even linear. Okay, so there's lots of examples I could show you. We have tons of examples from fluid flows. I'll just show a bunch of them here, where essentially you can learn a good coordinate system and sparse differential equations that describe how those variables co-evolve. But instead of diving into all of these examples, maybe I'll stop here for questions and see if anyone has any kind of questions. So thank you all very much for your attention, and I'd be happy to answer any questions you have. Thanks.
Thank you so much, Stephen. I think we have a couple of raised hands. Yeah, Guy Bart.
Hi, Hi, Stephen. Great talk. Thank you so much. I had a question that is more technical in terms of imposing the sparsity.
Yes.
So numerically speaking, when you impose a sparsity, you must be using some form of threshold that decides when a value is considered small or smaller than the threshold to actually impose that term to be actually zero.
Yes.
So I was wondering, how is this decision made? Because I was thinking about a simple example. If you take the Taylor series expansion, for example, let's say that we take a stupid dynamical system, not even dynamic actually, we can go to try to learn the Taylor series expansion of sinusoidal function as sinus x, for example.
Yes.
So this will have an infinite number of vanishingly small terms in terms of their coefficients. So how would Cindy in that respect make the difference between true zeros and terms that are becoming vanishingly small in the series?
Great question. Really, really great question. So I'll answer this question. What I'm first going to do is take a step back and describe what our sparse optimization procedure is, and then I'll answer that question. So there are dozens of kind of commodity algorithms to find the sparse solution x dot equals f of x now. Maybe the simplest or the oldest is the lasso algorithm, where you would just add an L1 loss function. Morally, it's a good idea, but in practice, it actually doesn't converge very well. So you might add a ridge regularizer like the elastic net. That's not what we do. So we actually have our own custom algorithm that we wrote down to solve this problem, which is very much like what you described. There is a thresholding step. So what we do is we first apply least squares. And when you find the least square solution, then this C vector is dense. It has all terms are active, but some of them are small. And so you pick a threshold and you kill most of those terms. Then you do another least.
How do you pick the threshold? How do you know what the threshold should be?
Yeah. So I'll get there. So we threshold, then we do another least squares onto the remaining terms. Now some of those are small. We threshold again, and we do this until it converges. So choosing that threshold is delicate. And generally speaking, there are a few ways we choose that threshold. If possible, we have holdout data and we do cross-validation. We withhold some of our training data as test data, and we see how good our model works on that test data. That's a pretty good way of finding this threshold, is essentially try all thresholds and then see how the validation error behaves. And there will be some minimum in the validation error. You can also do this with the Pareto analysis, where you look at training error versus complexity. And typically you have a direct crash. There's a sharp elbow in that plot of training error versus complexity. So those are kind of the two most common techniques we use, is cross-validation or a Pareto curve analysis. In the Taylor series example, that's actually a great example. We showed that in this first Cindy paper. That was actually an example we looked at. If you don't have the right library, if the function you're trying to model is only approximated in your library, your Pareto curve of complexity versus accuracy is going to have a soft elbow with lots of models. Linear will be a simple model, but the least accurate. Cubic might be in the sweet spot of accuracy and complexity. And then if you add, fifth and seventh and ninth, you get diminishing returns. So this is a Pareto curve. That's exactly the kind of trend we see in lots of physical systems. When we learn those new plasma models I was telling you about, that's exactly what we get, are kind of the Taylor series approximations of some nonlinearity we don't know how to write down yet. And so oftentimes what we do is actually swap out the library. We try different libraries too, with different generalized functions, Bessel's functions, trigonometric functions, polynomials, because sometimes those give you much sparser models and you learn the closed form solution.
Yeah, so that's great, because you actually went on. I had a follow-up question.
Okay.
My first question was basically, do you do some form of meta-learning for the threshold, which you answered. I guess for that you can use criteria like BIC or AIC or
absolutely, yep. Yep.
My other question is also another meta-learning question, which is, do you do meta-learning on the dictionary itself? Because the result that you get is structurally highly dependent on the choice of the right dictionary terms that you allow your system to play with.
Yeah, that's exactly. And the answer is yes, we do, but there's a lot more we could do. So we could play a game. Imagine we don't know that there's a function called sine of x. How would we, from this procedure, learn from the Taylor series expansion, the closed form solution? That's something we don't have a solution for yet, but we're working on that. So we're working with our colleagues that do genetic programming to try to kind of combine genetic programming with this sparse regression procedure.
Yeah,
I
guess as long as you work in a complete basis in terms of the dictionary terms that you choose, then you have universal representation of other functions as well. Thanks a lot.
Awesome, thank you.
Cheers.
Excellent. Other questions?
Yeah, Marta has a question.
Thanks very much. Thanks for the rest of the talk, which was great as well. Very similar to the question that's just been asked. I didn't quite understand whether you predefined the number of coordinates that you wanted to have, or whether that was something that you learned as well, the optimal number of coordinates. And then as a follow-up question, I was wondering how Cindy coped with noise in the data, and whether you had to have any special regularization for that, or I see it there.
Great questions. Yeah. So how to pick the right number of variables, for example, in this latent representation Z, is actually, so it's not too challenging. Typically what we would do is we would first train an autoencoder without the Cindy model. So we would just try to fit the data without modeling the data. And we would do the kind of normal hyperparameter tuning that we would to tune an autoencoder. So we would do some, have some cross-validation to look at the error versus the number of latent variables. Very similar to how you would pick the number of clusters in like a k-means clustering, something like that. So that's actually not too bad. Noise is a very interesting challenge. So Cindy is highly sensitive to, pretty much all of these modeling techniques are sensitive to noise, especially if you have to compute the derivatives on the left. And so there are probably a dozen or more papers, maybe 2 or 3 dozen papers, just trying to address noise sensitivity in Cindy. One of my favorites is what's called integral Cindy, where essentially you can integrate both the left and the right-hand sides of these equations. And that is a huge help for noise. For partial differential equations, you basically integrate over control volumes, and that averages out the noise dramatically. We also have a recent paper where we use ensembling and bootstrapping. So essentially bagging and robust bagging to do lots and lots and lots of Cindy models. We basically build like 1,000 Cindy models from subsets of the data, and we look at distributions of where the terms are, and it gives us much, much more noise robustness than before. So, in some cases we can handle a few 100% noise, which if you look at the data, you can barely tell that there's anything there, which is kind of cool. Yeah, great question.
To do the whole process of running. The bootstrapping process must be very lengthy and
well, that's the nice thing, is that for these problems, these regression problems, the Cindy is very, very fast, because we're essentially doing a least squares on theta. And that's blazing fast for moderate dimension problems. So, we can do a bootstrapping, like a bagging Cindy for something like Lorentz with an ensemble of 1,000 elements in seconds. So it's really, really fast.
Thank you.
Yep. Other questions?
Yeah, we have Claire.
Hi, Stephen. No, thanks for the talk. That was very interesting. I just had a question about about the slide where you showed the Cindy modes versus the pod modes for, I think it was lid-driven cavity flow. And I wondered if you used, that one, if you used autoencoders, would, say your Cindy code picked out 3 modes, would your autoencoders then also be able to identify those 3 sparse modes, or would you actually need a few more modes than that if you're using autoencoders? Is there some?
That's a great question. This is fairly preliminary work, but I'll show you just a little bit of what we have here. This is with Jared and JC. So if we take that cavity and we crank up the Reynolds number so it's a little bit more complicated, then the POD analysis would say that we might need 50 modes. But the autoencoder, because so the POD subspace is linear. So we need 50 of a subspace of 50 dimensions to capture this data. But the data live on a submanifold in that subspace. And it turns out that that submanifold is only 4-dimensional. And so the Cindy autoencoder actually learns the 4-dimensional submanifold of this 50-dimensional space. So it's a pretty massive reduction in dimension. Enough of a reduction that we can actually learn models on that manifold. So it was 50 is too high for us to learn Cindy models, but we can learn them on this 4-dimensional submanifold. So at least in this case, the autoencoder manifold learning gives us a pretty dramatic reduction in dimension.
Mm-hmm. Yeah, and did you find with your autoencoders that you can learn, you can get down to 4 modes, you can train so that you do find those 4 modes?
So this example I'm showing is, it's not a unstructured autoencoder. We're not really using an autoencoder to learn this. It's more, we're learning this kind of by hand with a lot of physics knowledge. We know that there are these triadic interactions from the physics, but it is kind of a proof that there is a structure like an autoencoder that exists that goes down to 4. So this is promising that we hopefully could, with an autoencoder, learn these 4. That's the next thing Jared's working on, is trying to, in an unstructured way, learn this manifold. So this has a lot of prior physical knowledge to show that it can be done. Now we need to show that we actually can do it. Yeah.
Yeah, great. Thanks, Steve. That's
Cool.
really interesting.
Thank you.
Thank you, Claire. We have Rosella.
Yeah, but just if we don't have other questions.
Okay, can I have one tiny question? In terms of scaling this, for example, you show like a flow past the cylinder, the Lorentz attractor. If we have like a real case scenario of simulation with like, let's say, millions of points, how will this like scale up in terms of like computational time? Do you see any problems with this scaling up to several? No.
Yeah, so there's certainly some scaling issues. I mean, this system here has 100,000 degrees of freedom, so it's not small. But going even higher than that, there are a few things we can do. So we have a stochastic version of this that applies to turbulent systems. So we can essentially model the large coherent structures with Cindy, and then also learn the stochastic correlated forcing of the turbulence. So that seems to scale well. And I also think that this autoencoder is a way of going to more complex systems. So that's kind of the short answer. I think if you get into a really, really, really turbulent scenario, we're not going to learn all of the turbulence, but we might be able to build models of the coherent structures.
All right, cool. Yeah, thank you. Yeah, Rosella, go
Yeah,
ahead.
for me was actually, I have several questions, but I will give too deep in the details, and we are running definitely out of time. But at the beginning of the talk, we were mentioning, future opportunities to meet in person. And in that context, I will like to share with you an event we organize every year as part of the International Conference of Computational Science, the ICCS, which is a ranked conference. It's a top conference for computational science. But within the conference, we organize a workshop on machine learning and data assimilation for dynamical systems.
Cool.
So it's, I think, the perfect, and this is the 4th year that we organized that. And over the last year, the first year we met in person, then for 2 years we met virtually, but still we have like, the community has increased quite a lot. And I think we all can have, let's say, very great benefit from having you or your group, part of your group, attending to the event. So I would like to share with you the information about the
That sounds great. Yeah, that sounds really exciting.
Yes, so I will share my screen, and then I think we will send you this information. So just to let you to know that I received an email yesterday from the conference. The deadline will be extended of a couple of weeks. So
Okay.
don't worry, because the deadline was now the 21st of January. But we accept abstract. So just if you want to, as today, you want to share your work with the community, we have also people from the ECMWF, from NCAR. So we have people coming from also operational, let's say, centers, and usually. And so in abstract, or there is the opportunity, I was mentioning the abstract together with the operational centers, because usually they cannot publish paper in conferences. But then we also have 2 papers that can be published on lecture note in computer science, 7-page papers, so short version, and 14 pages paper, so long version. And they are both published on lecture note in computer science. So in case you are interested in that, the deadline will be definitely extended. So we will have, let's say, from now, other 3 weeks to close the works. And yeah, and we will send you the link. So in case you are happy to join us, the meeting this year will be in London.
Wonderful. And could you remind me the date for that?
June.
June. Oh, so that's excellent. I'm planning on being in Europe in June. I have 4 conferences I'm going to, so the time is a little tight, but I'll be in kind of between Lisbon and Scandinavia, back and forth. So not too far.
We are in the middle.
Yeah.
Between Lisbon.
Okay, yeah, no, that sounds like a lot of fun. So yeah, depending on the dates, and I can also suggest some other people from the group that might be interested.
21st, 24th of June.
Okay, excellent.
We will send you all the details, and also in this link there are all the details. And finally, before closing, I think today we really finished late. We have another call for journal papers for a special issue on machine learning and data science for dynamic systems. The deadline is the 1st of March. The journal is Physica A. So we will send you both links in case you are interested. Your contributions are very welcome. You Wonderful. And all the people attending to the meeting. So happy to have you.
Awesome. Thank you so much for having me today. This was a lot of fun and great questions, everyone.
Oh, well, thank you for giving us a bit of your time to explain all of the fantastic work you've done.
Yeah, thank you.
Awesome. Well, have a good rest of your evening and hope to see you soon.
Yeah, have a lovely rest of the day. And yeah, thank you so much. Bye, everyone.
Bye-bye.
Bye.